So now let us go on to the, actually, as usual, I flashed up the slide and then I'm going to hide it from you. So let's go back to our various problem settings, right? So we just figured out what to do when the network structure is, we just figured out what to do. Excuse me here. We just figured out what to do when some of the data is missing. Okay. But now let's go back to assuming that we have all the data, right? So there's no difficulty there, but the difficulty that I have is that I don't know the structure of the Bayesian network. This is the more interesting problem, right? We don't just want to learn the parameters of the Bayesian network. We want to learn the structure if we can. Right? So how might we do that? Any suggestions? Well, think about it. This is going to be a discrete search type of problem, right? It's like we're trying to learn a structure at this point, right? Parameters, usually we do continuous optimization in one form or another, right? But this is more like learning decision trees and rule sets, right? I'm trying to find what the structure of the Bayesian network is, right? So this is probably going to be some sort of search process, right? Where I search over structures. Right? At any one point in the search process, I have a structure, right? And I can quickly fill in the parameters, right? Because there's no missing data, so one sweep of the data does that for me. And in fact, if we do this cleverly, I don't even need to recompute all the parameters as I change the structure. But how might I do the search for structure? Okay, let's think about this, right? Well, let's see. What do we need to do search? The first thing is we need an initial state, right? If you're trying to learn the structure of a Bayesian network, where might you start? What might be your initial structure?
Everything plus everything.
Everything what?
Everything does everything.
You mean arcs between everybody? That's one option. It might not be a very good one. Why?
Because it's going to be really computationally expensive to figure anything out.
Yeah, I'm going to have some very large tables to estimate there. Right? It's not just computationally expensive, it's going to be unbearable from the point of view of the sample. Right? Some node in there is going to have all the others as its parents. So what's another option? So this is a little bit like forward and backward selection and tree pruning and post pruning, right? In this case, the backward version is not going to be, very good, right? But what's the other option?
Start with nothing.
Yeah. I start with nothing, right? No, this is a joyfully, efficient Bayesian network to start out with, right? Is you assume everybody's independent. There are no arcs in the network. Okay? And then estimating all my parameters is going to be very quick. And then what I'm going to do is I am going to add arcs where the data demands that I add them, and nowhere else, right? Adding arcs is expensive. Remember, the cost of storage and the cost of inference may go up exponentially with the number of arcs that I add. So I want to be pretty conservative about adding arcs. So it's good to start with an empty network and then just refine it. Okay? So how might I refine it? So question 2, right? So I have an empty Bayesian network. So what kind of search operators might I use now? Right? What might you want to do? What is a natural search operator when building up a Bayesian network starting from an empty one?
Some sort of correlation with.
Absolutely right. You want to detect that, say that, let's say, for example, that we were learning the Bayesian network in the example that we just saw, right? So we had A and B and C, right? Empty network. What do you want to do here? For example, that B depends on A, right? So you want to allow yourself to add an arc from A to B. And then maybe you want to allow yourself to add an arc from B to C, right? So what is a good operator to have? Add arc, right? Right? Don't try to be very deep about it. This is very simple, right? Think of it as a graph, right? I'm building up a graph. The graph starts out empty. I want to have some edges in it, right? Assuming there's going to be, some non-trivial, structure to learn, right? My operator can just be add an edge. What should be my, so I have this simple operator, add edge, right? So what I can do is I start out, this is a little bit like learning, decision trees and rule sets, if you think about it, right? Instead of adding antecedents, I'm adding edges, right? So what might I do? I can look at all the possible edges that I could add, right? and I score each edge, right? And then I pick the best one, add that to my network, and then I repeat and add another edge, right? And little by little, I can learn a very good Bayesian network if things go well, right? But there's something very important that I have to be careful here as I add my edges. Something I didn't have to worry about when we were learning decision trees and rule sets. What might that be?
Cycles.
Sorry?
Cycles.
Cycles. Yeah, cycles, right? If I just do this, add edge, add edge, there's nothing to prevent me from doing this. And what is a Bayesian network with cycles? It's nothing. It's meaningless. Remember, a Bayesian network is just a clever way to take advantage of the chain rule. The chain rule implies that there's an ordering for the variables, and you're, putting them into the product using that order. If the graph has cycles, I don't know what that means. I don't know what kind of chain rule application that maps to. Okay, so I have to forbid cycles. So at every step in the algorithm, as I look at adding more edges, I have to exclude the edges that would create cycles. This is very unfortunate because as the network grows, as you can imagine, it becomes expensive to check that this new arc will not create a cycle. But there's no choice. I have to do that. Okay. So next question: how do I evaluate? Right. Let's say I'm trying to decide whether to add an arc from A to B or an arc from C to A. Right. How do I decide which one is better? How should I evaluate my arcs? In some ways, this is the most interesting part of this process because the rest is kind of straightforward ideas, right? How should you evaluate it?
Higher degree of dependence.
Correlation.
Yes, correlation. That is absolutely the right intuition, right? I want to add an arc between A and B. Maybe that should be the first arc that I add if the correlation between A and B is the strongest that I have in my data. Okay? So how might I measure that correlation? Well, one thing that I could do is actually measure the correlation, right? So one approach to building Bayesian networks actually does just that. It measures correlations between the variables, and it puts arcs where there are strong correlations. You can use things like significance tests, right? So like, is this correlation that I'm observing in the data significantly different from what I would observe if there wasn't any? And those arcs I add, otherwise I don't. Okay? But another thing that you can do, which is the most frequently used one, is to just measure the likelihood. Right? Remember, when we were learning, think back to the basic idea of Bayesian learning, right? Or statistical learning, right? Is I'm trying to learn a model, I'm trying to learn a Bayesian network that has the maximum likelihood, right? Or that has the maximum posterior probability, right? And when we were learning the parameters, right, when we were doing EM, right, we pick these values because they're the maximum likelihood values. If I have 100 examples and in 50 of them B is true, right, then the maximum likelihood estimate of the probability of B is 0.5. And that's why I choose 0.5, right? And now we want to apply the same idea, right? We should be consistent, right? This is statistical learning. I still want to maximize my likelihood, right? So what I should do is I try adding each edge to my network, right? And then I measure the likelihood of the resulting network with the maximum likelihood parameters, right? Simple idea, and again, that can be done fairly efficiently. And if you're careful, about caching things and whatnot, you can avoid redundant computation, and it's going to be pretty fast. Okay. So the basic criterion that you can use for this is maximizing likelihood. But do you think that really is a good thing to use? What might the problem with that be? This is where we get to see a deep understanding of machine learning.
Overfitting.
Yeah, overfitting. Brilliant insight. Why might overfitting be a problem if using maximum likelihood for structural learning?
Because you maximize the training data.
What's the maximum likelihood structure? Right, we can ask that question, like, what is the maximum likelihood structure? Can anybody guess? This is where you really see how bad things can be. The maximum likelihood structure is guaranteed to be the completely connected structure. Others might tie with it, but you can never do better than with a completely connected network. Why is that?
Completely connect. What do you mean by completely connected?
There's an arc from every variable to
Every other one.
Yeah. So, but remember, you can't allow edges, right? So what this would mean here is something like this. Let me do it graphically, right? Let me just draw the nodes in a line, right? So what is a completely connected legal Bayesian network, right? Is, let's say, this is x1, x2, etc., xn, right? x1 is a parent of x2, right? And so let's do this the other way, right? So x2 has x1 as a parent, and then x3 has x2 and x1 as a parent, right? And then x4 has all of them, right? And then finally xn, all of the preceding ones. So the idea is that each variable has all the preceding ones as parents, right? Meaning the Bayesian network didn't buy you anything. This is just your banal application of the chain rule. But this is what you want to avoid like the plague, because inference here is going to be impossible, and also learning is also going to be impossible, unless it's a very small network, right? So my question is, why is this the maximum likelihood, or to be precise, why is this guaranteed to be a maximum likelihood network?
Because any smaller network you could represent like this by putting 0 entries in your tables.
Exactly. So imagine the real network that generated this data, right? The real network that generated this data has some arcs somewhere, but doesn't have arcs in other places, right? And if I'm missing one of those arcs, then I'm in trouble, because there's a dependence that I can't represent, and I lose likelihood because of that, right? There's a correlation, and the variables look like this, but I'm not able to model that. Okay? But if what I do is add spurious arcs, right? Those spurious arcs don't reduce my ability to model what's going on. They just mean that there's going to be duplicate entries in the tables, right? If there, for example, if there's, let's say that x3, should only depend on x2, but I've also put in x1, right? What that means is I'm going to have the same entries for the table for x1 and not x1 for each value of x2, which is terrible, right? But it's still a maximum likelihood model, right? So, did everybody follow this? So doing maximum likelihood learning for parameter estimation is already problematic, right? This is why we do things like Laplace estimates and M estimates, right? To make sure that small counts don't make things unstable. But for learning structure, it's a much worse idea, right? So learning structure using likelihood is a terrible idea. So what do we use instead of likelihood? Think back to the very beginning of, this part of the class when we started studying, Bayesian learning, right? We saw that maximum likelihood learning is actually a special case of what? MAP, right? You remember the acronym, but can you remember the content? Hey, remember the acronym is the first step, right? So what is MAP learning?
You make your hypothesis.
Prior probabilities were
Exactly. I pick my hypothesis that has the greatest what?
prior.
Not just prior, remember, Bayes' theorem, there's the prior and there's the likelihood, right? And when I do the product of both of them, what do I get? The posterior probability, right? Which is the probability after I see the data, which is a combination of how much I believed in the hypothesis before seeing the data and the likelihood, okay? Well, this seems like a good thing to use here, right? And the way you avoid overfitting is by having, a good prior, right? As always in machine learning, you can't escape the need for some knowledge, right? So what might be a good prior? Or you can also answer the following slightly different question. What do you think is a prior that people commonly use, or a type of prior that people commonly use? Uniform prior, bad idea, because what? Why is that a bad idea? What happens if I'm doing MAP learning with a uniform prior? This becomes equivalent to what? Maximum likelihood, right? So that's probably not the answer. So what might a non-uniform prior be? Let me give you a powerful hint, right? I don't want to learn a Bayesian network with a lot of edges, right? Edges are costly both for learning and for inference, right? So what do I want my prior to do?
Number of edges.
Yeah, I want my prior to prefer networks with fewer edges, right? The idea here is that, I will put in an edge grudgingly if the data tells me it's there. But that means that it has to clearly be there. If it just might be there or not, Nah. So what I can do is I can have a penalty on the number of arcs in the network, or let's say the number of parameters, some sort of complexity penalty, right? Let's say an exponential penalty, right? And so what that means is when I take the log and sum, right? Remember, it's always good to do that. What I have is a constant penalty per edge, right? And I have the log likelihood term. And now what has to happen is that when I'm considering adding an edge, the log likelihood has to increase by more than my edge penalty. If the penalty on my edge is lambda, and the likelihood goes up by less than lambda, then I say, nah, not worth it, not worth the trouble. If the edge penalty is lambda, but the likelihood goes up by more than lambda, well, then I'm willing to pay the price because it's probably a net gain. And of course, by tuning, this lambda parameter, right, I can go all the way from learning a very sparse network to learning in the limit, if my lambda is 0, the maximum likelihood one. Okay? So this lambda is the parameter that you probably want to tune by cross-validation. Okay? Now, this is one option for a prior, and this is the lazy option, and we have lazy tendencies in machine learning, so this is very widely used, right? But what might be another option? Let's say that you actually know stuff about this problem, right? You are trying to learn a network for you're a park ranger, right? And you're trying to learn a Bayesian network to predict forest fires, right? And you've decided that these are the important nodes, right? And you're a park ranger, you know a lot of stuff about forest fires, right? Do you really just want to use a prior that just says you prefer smaller networks? Are you that lazy? Right, what might you do?
Draw one.
Draw one, exactly. This is actually one of the greatest beauties of learning Bayesian networks is that it provides a wonderful way for you to put in your knowledge. The way you put in your knowledge is you draw a Bayesian network. Now, when we were not learning the structure of the Bayesian network, the problem was that structure that you put in, you were stuck with it forever. And people are often good at kind of figuring out who depends on who, but they're not perfect, right? They can be off, right? They can miss things, they can get things wrong, right? The ideal thing that you want to do is you want to be able to put your knowledge into the initial Bayesian network, right? This is your best shot at what's going to happen in that domain. But then you should allow the data to say like, hey, there's this arc here that's missing. The data tells me that there should be an arc here. I'm going to put it in. Or the data could also say, you put in this arc, but I don't see it. So let me take it out, right? Which means that you need a new operator, right? In addition to having an operator that adds an edge, if you're going to start with a Bayesian network that is not empty, you should also have an operator that deletes an edge. Okay? And then what you can have is a prior distribution that penalizes moving away from the initial network. So now what I can have is a penalty for every arc that is different from the initial network. If I add an arc, I pay lambda, but if I take out an arc, I also pay lambda. So again, the data can let me move away from my prior, the network that I believe in, but again, that data had better be strong, have strong evidence that the arc needs to change. And I can use my lambda to say how confident I am. If I really believe in that prior network, I have a very high penalty on changing edges. If I really don't have a lot of information, it's just like something that I drew quickly and I'm really not sure well, then the lambda can be low and the data can allow me to move away from that fairly easily. But even in that case, starting from that point is probably a very good idea because again, we're in a very large search space full of local optima, so having a good initialization point that exploits your knowledge can be the difference between success and failure. Okay? So this is what you really should do is put some thought into drawing your initial Bayesian network, or ask the expert, right? You can interview the expert, and you guys together can draw a Bayesian network for the problem, right? This is the kind of thing that people do all the time. And then you go and use some data to refine that. There's one more operator that people often use besides adding an arc and deleting an arc. Can anybody guess what it might be?
Swapping ends.
Yeah. Well, swapping, I'm not sure what you mean by swapping, but here's how I choose to interpret that. It's taking an arc and reversing it. This turns out to be a very useful thing to do, because what often happens is that people put arcs in the right places, but they often put them in the wrong direction. Wrong direction means there isn't necessarily a wrong and the right direction, but they often put it in a direction that makes things harder from the point of view, of making the learning easy and the inference cheap and whatnot. Okay? So, and if you think about it, reversing an arc, right, is just the same thing as deleting one and then adding another one in the opposite direction, right? So why do we need this operator? Why can't we just have add and delete, right? Why is it useful to have reverse? It's actually
less of a
Yeah?
penalty, because you've got something now, it's just not the direction.
The problem is that when I take out, remember, these are two variables that are strongly correlated, right? That's why you put an arc between them. What happens if I take out the arc? What happens to the likelihood? It really goes down, right? Because now I'm saying there is no dependence. And then I put it back in the other direction. But the problem is that to go from this likelihood to this somewhat higher likelihood, I'm going through, an intermediate stage that has a much lower likelihood, and that is bad, right? That is a barrier that's going to prevent you from doing that. So the reverse arc operator is really there to overcome the limitations of this greedy kind of search that we're doing, right? It's going to allow me in one step to jump from one peak to another higher peak without having to go through the valley in between, because the greedy search wouldn't do that. Okay? So yeah, so at this point, see, we have all the pieces. So here's what we can do when we have a known structure. We have a search process. My initial state can be my empty network if I don't know anything about the domain or I just don't want to bother. Or it can be a prior network, right? That is often called the prior network, is the network that the experts design a priori. And then I have operators like adding, deleting, and reversing arcs. And then my evaluation function should be the posterior probability, not just the likelihood. And again, this posterior probability is going to have a prior probability that's going to penalize you for diverging from the initial network, right? Whether it's a network that you've designed or the empty network, right? If you think about it, this idea of penalizing, adding and removing arcs from the original network, it works just as well if the initial network is empty, right? In that case, it's just a penalty for adding arcs, so that doesn't even have to change. Okay. Now, there are many more variations of learning Bayesian network structure. It's a very active research area, but these are the basic ideas. Right? If you needed to implement the Bayesian network structure learning today, you could do it. Questions?